Greetings and welcome to Chemistry A in the AF. I'm your host, Mr. Shindelka and Hot Dog. We got an out-of-sight class here today. The weather's beautiful. It's 15 degrees outside. Traffic's running smoothly on College Avenue right now. Now, are you guys ready? Buckle up. Let's get a review of the work you did at home, electron configurations. And you wanted to do something that involves an F over, right? And if we go over an example, will that probably help you out?
Yeah.
Okay. How about
Can we do you?
uranium? Sure. Is that on the assignment?
No, it's on like your notes.
Okay.
Like,
Okay. I was just wondering if you were like trying to pull one out of me.
I should have done that.
Gosh, you wasted your chance. Okay. Uranium it is. This one was already done, but on work today, please, machine. Uranium. Now, I'm going to be pointing, I'm saying this on the video here. I'm going to be pointing to the periodic table that you can't see, but the students live can't see. Uranium is in the, you guys see how this periodic table works? These would be inserted in here, in this space here, but it would just make it push two pages wide. That's why it isn't. It falls here. This is where the LULR, like, you see what I mean by that? That's why it drops down, only so that it fits on one page. So uranium is in this row. See the 1, 2, 3, 4, 5, 6, 7. So what I think is I count the row that uranium is. And I just say to myself, 7th row. Now, without using the boxes, because I know that the 7th row starts up here, but without using the boxes, how do we do this? Well, we say uranium's in the 7th row, so it has everything that the 6th row has, and nothing has changed. So the 6th row ends with, you look at the periodic table, Rn. Radon, right? So we do a shortcut because we do not want to list all of those boxes. So our shortcut starts with Rn. That means everything in the 6th row and before. There's no reason to count those electrons again because chemistry really only involves the outer shell electrons. Then we go back to the periodic table, and I start at the 7th row. And the shortcut is that this area is always S's. Do you guys recall this from the video? So 7S1, 7S2. I count across my S block. Now we do a detour. We go all the way down. So I think of this as a double drop. The D's are always drop the number once. This is even further below, so drop the front number twice. 7, 6, 5. We drop down to 5. And then I count up to uranium. That'll be 1, 2, 3, 4 electrons. Does that make sense? If you Google it up, you might get a variation of that. You will. Don't worry. We're using predictive. And I sometimes use ones that I know if you Google up, they'll get them up a different way. Then I can tell if you're actually thinking it through or if you're copying from Google. So you get something different. Okay. This is the F block. And the D block is here. The D block, whatever row you're on, you drop one number. If this is 1, 2, 3, 4th row, tell us, like potassium, 4F or 4S1, 4S2, 3D1, 3D2, 3. But then when you get to the F's, it's drop 2 numbers. Now, I'm going to do one that involves a little bit of everything. Let's do, why don't we do radon, actually, as an F. because that one's done. It's actually good. Let's try RM. RM, I pointed it out before, is at the end of the sixth row, right? So you always look to the noble gas from the previous row. The fifth row ends with xenon. You ever watch that show, Xeno Warrior Princess? Never heard of it? Google it up sometime. Warrior Princess. Xenon. Okay. So I say XE. End of the fifth row. Now we do the shortcut. It has all the electrons, 54 electrons, just like xenon does, but then we're worried about the outer shell electrons. So I start at the sixth row, and I say my S block. I count 1, 2. Sixth row S2. Then I follow my line on this one. And it's a double drop in numbers. So what is this going to be for the F's? 6 down to 4. There's 14 across. This one's stupid. 4 down. 14. Then the tedium comes back up here. I've got my D's now. And the D's only drop the number once. So instead of 6, we use a 5. D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to mercury. 5 D. Then the P's, the number always matches what the S, the row. So then we get up to here. I'll say P. 1, 2, 3, 4, 5, 6. 6, row, 6. Now what I just did there, I'll just point out. I'll let you get it. Look at this. Sixth row. Well, we said it has everything that happens before. We counted through the S's. Then the next were the F's, right? This is just a clear name, so it's going to go. Then we counted through the D's. I'll just say we counted through those, right? And then we counted through all of the P electrons. That's what I did as a shortcut, though, without referring to the boxes. Because the periodic table is arranged that way. Exactly. Yeah. Helium is so easy because it's first row. And it's 1, 2. S, 1, S2. That's the only exception as far as you notice in this electron shortcut thing, is that the helium is the only S on the right. Everything else are S's. You just count sideways across your row. You don't need that sheet. And that's what I'm getting you guys to work at. I want you to understand that it's done by energy levels. But it so happened that the periodic table, they organized it for different reasons. But when electron configurations and stuff were discovered, invented, the idea and stuff, it all fit in perfectly with the other aspects of the periodic table. That's why you got these big blocks of F's, D's, and F's, or P's. Okay. Other questions about the homework? Yeah? You're only going to find valence electrons for, well, okay, but you'll only be required to do them. They're only really meaningful for non-metals. I don't have one on the do I? I'll just do the shadow box. The shortcut for valence electrons is, of course, it's the totals of S's and P's only. But let's say you got iodine. Now this, for you at home, iodine's way down here. And yes, you don't want to do the electron configuration. It's in the 17th column. So I just say 17 minus 10. Just drop the 1 in front of it. It's got 7 valence. Whatever the row number, or column number. Not row. Oxygen's in the 16th column. Sulfur's in the 16th column. They have 6 valence. Nitrogen and phosphorus are in the, well, when I do it all, it doesn't. 15th column. 5 valence electrons for those. Carbon's in the 14th column, 4 valence electrons. So you get the number. And hydrogen and beryllium, rows 1 and, or columns 1 and 2, those are just 1 or 2. Okay. So that's a quick short. Other questions about home material? Okay. Then we work on some equilibrium stuff. Yes, so I'll flip screens. I'll pause the video recording. Hello, those of you online. This is a skill we need for our equilibrium chapter, calculating concentrations and molarity. I'm going to get you to pause your video and jot this stuff down in the next few seconds, and then you can unpause the video when you're ready to roll. Okay? Concentrations, molarity. Okay, by now you've printed or copied this out. I'll read over it real quickly. Molarity measures concentration with moles of solute dissolved in liters of salt. So this would be like sodium chloride, table salt, most sodium chloride, dissolved into liters of water. In our class, you can assume if it doesn't say anything, it's always dissolved in water for calculations, unless they tell you. So the example we're going to work through is find the concentration of 0.4 moles of sodium chloride dissociated in 2 liters of water. The word dissociated, you can almost think of it like dissolved. It means something different, though, chemistry-wise. But today, think of it as dissolved. We'll get into what that means. What I wanted you to start with is square brackets, has to be square brackets, NaCl. The fact that it has square brackets means concentration, moles. What do? Uh-oh. This is where it was screwing up the other day. I'm going to pause the video. And we're back. Hopefully it's recording. Yeah. Now, so that's sodium chloride. If we want molarity, it's moles divided by liters. We got, and this is a pretty simple question on purpose. So 0.40 moles of NaCl divided by 2 liters. So that's it. As far as the math part of this, that's simple. Paint sheet ready, it's simple. So 4 divided by 2 is decimal 2. 1 decimal. Now, I can write down moles per liter, and I actually do quite often. But if you want to abbreviate that, the same answer, equivalent is, this is okay because one mole per liter is the same as 1 big M. That means moles per liter. It's just an abbreviation. So if you see big M there, it's just so you don't have to write down moles per liter. Okay? Either answer is fine. I would have probably stuck with the first one. Okay? But this is good too. Well, motor it on. Give you a little bit of time to jot this down. Pause the video, jot this down. I'll start it up. We're back. Calculate the concentration of sodium chloride when 10 grams are added to 750 water. Now, looking back at our previous example, we need moles divided by liters. We can get moles of sodium chloride from the grams. This, I think we can just do in the head. Milliliters to liters, how do we do that? How many mils in a liter? 1,000 mils per liter. So, a lot of milliliters makes up a liter, 1,000. Divide by 1,000. That really just turns into moving the decimals. You ever stop it in my classroom? Ask me. I also have it up there, 1 liter, 1,000 mils. Come on, please work. Shift it back. Okay. So the first thing is we need moles. So we're going to calculate. The way I do it, typically I start with what we're given, 10 grams. Sodium chloride. Then I look up sodium and chloride on the periodic table. There's only one of these, not Cl2. So I add up the sodium, 22.99, and the chloride, 35.45, and I'll give this down. The thing is to get to moles, what do we have to get rid of? That's what I put on the bottom. Yeah. So there's grams on the top here. I want to put grams down here. Grams, I want the mole on the top. Then when I add the sodium mass and the chloride mass, I get 58.44. That's it. Now this is straight across type. You really have to say times 1. You just divide. 10 divided by 58. And you get a little breakdown. I'm assuming you guys know how to use calculators. Times are canceled, so we have that many moles of sodium. I think we're ready now to do the molar chemicals. So you take this. Sodium chloride's concentration is what we want. We take the moles divided by liters. I've already listed the chemical on the left, NaCl, square bracket. Rather messy. And 0.75 liters. Now I did that conversion in my head. We talked about that earlier. Divide it out, 0.2. I'm going to keep just as moles per liter. I could put biggie on the phone. Pause. Okay, can you get out your worksheet for this section 2? And it'll have this list here. Obviously, there'll be no marking. Awesome. Now take a look at this. This time the chart has no question mark. Go ahead. But you notice, and I'll see if this pen works. The two reactants, Cl2 plus PCl3, they're always at the same thing because they start at the same thing. And they're 1-to-1, so they change the same amount each second. So when we graph it, you only need to just consider Cl2 or one of the. That's why I circled that. As the Cl2, the reactant goes down, it only makes sense that the product produced or made goes up from 0. That's one. What I want you to do is below, there's a grid. Draw a graph of this reaction, concentration, reactants, products versus time. Smooth fit between the points indicating the concentration. Label which line corresponds to which substance. So your graph. Time is on the bottom. 20, 40, 60, 80. Start with 0. So on. you count, and I'll show you quickly here, but I'll do it this way. Want to see how I set mine up? Oh, there we go. See how I space mine? You can space yours like that. And then plot your two things. One starts at 0, one starts at 1.0. I'll get you guys a minute or two to plot your graphs, and then we'll compare what I have and what you have. So you graphed your stuff. I chose Cl2. It didn't matter if you chose PCl3. Same thing. It starts high and then goes lower. The product, PCl5, I have in red, low, and then it gets high. The example we did last week with the graph, crisscrossed, right? And I did a sketch. These don't have to crisscross. It had nothing to do with equilibrium. But the question A here is, when was equilibrium obtained? 80 seconds. Why 80 seconds? Because this is the point where everything is leveled out. It doesn't change out. That's what I'll get you guys to look at the second side of the page, and we're going to fill in this question. Remember last week we went to a chart at equilibrium, how things change and stuff like that. Well, this is what this is. Let's take a look at this reaction here. N2 plus 3H2, 2NH3, that's ammonia. 2 ammonias are made. On my chart itself, I'm going to fix those headings a little bit. N2, that's a 1 on the balance. One group of N2, plus 3 groups of H2. I'm drawing a line here to separate the products from reactants, because if one goes up, the other goes down. And 2 ammonias. That tells us the ratio of change. Nothing else, just change. Let's just take a look here what happens. So, look from 0 to 1 second. I'm going to draw in the change arrow. You go from 1 to decimal 9, that's a change of negative 0.3. Now, go figure. 0.9 minus 1. Drop. Now, this has a 1 to 3 ratio. And they're both reactive. So if one goes down, the other goes. If nitrogen goes down by 1, then hydrogen goes down by 3. So let's think this through. If nitrogen goes down by decimal 1, then hydrogen goes down by 3 times that. So minus decimal 3. Decimal 3. See how that worked? Now let's stretch this out a bit more. Produced the products. If the reactants are going down, that means it's making more products. So what goes down on the left goes up on the right. And in a 1 to 2 ratio. So if nitrogen goes down by decimal 1, the ammonia goes up by twice as much. See how the arithmetic worked there? And that line was all figured out there. I don't even see that. So let's take a look how this next line should appear. Where can it dissolve now? It's not dissolving, is it? All B. Which one dissolved? Well, the last one I did. Well, this border should go in screw. Okay. One hell of a hand. Decimal 9 and decimal 8. That's also down 0.1. So you know what? The next one will go down by decimal 3 as well, 3 times as much. And the last one will go up, instead of decimal 1, it will go up by twice. So let's just do the arithmetic. 0.7 subtract 0.3, we have decimal 4, right? 0.2 and add 0.2. Now, pretending we didn't know. And of course you have the answers, don't scratch them up. Let's just reason through this. This went down by 0.75, that's 0.5, right? It goes down by 0.05. How much should the H2 go down by? So 3 times 0.5 is 15. Minus 0.15. When I look at this, 40 minus 15 is 25, right? Decimal. And using that same reason, going down by 0.5 for the M2, twice as much of an increase. So 0.5 times 2 is decimal 1. So decimal 4 plus decimal 1 should give us decimal 5, and it does. Can I get you guys to do the remainder of the chart then? Same reason. Figure out 75 down to 72 is a change of minus whatever. 3 times as much, 2 times as much. Go through that. I'll give you guys a little video time. Pause the video and work it through it. I'll join the other one. Okay, I'm going to take a look at some of these with students. I'm recording. 75 to 72. I'm going to specifically ask you guys, I'm going to punish you just to.
It's 0.03.
That's down 3. Now, between N2 and H2, it's always a 1 to 3 ratio for the change.
Okay.
So what's the change going to be on the next one?
What is the 1 to 3 ratio?
Well, if I lose 2 on this column, I lose 6, 3 times more.
Okay.
So if I lose 0.3 on this column, I lose 0.9. Yeah. So 25 minus 9.
It would be 0.09. That's not what we subtracted from. 0.09.
Exactly, because that's 3 times the 0. 25 minus the 9 is the
0.6.
yeah, 0.16.
And so then for the next one, it would be 2 times 3. So then it would be
0.6. 3 times 2 is 6.
Yeah.
So 56. Got it. Now do the next one. Sorry, I thought it was cut. It's not music. We'll just zip through these while you guys are finishing off if you need to. 72 down to 70 is 02. Three times 6. 16 minus 6 is 10. Lastly, the 56, and you add 2 times 2, 4. What do you notice about the last line? No idea of an NH3 on the last line. 60 to 60, what's the change? Nothing. Same thing. Government from Mother's Day. Nothing. Same thing you're going to last year, too. Now she has a matching set. So if that didn't change, well, will it? I'm actually kidding. I got my Mother's Day. Hope you guys did too. If you have a chance and you're lucky enough to have them. Okay. last question. We filled in the check marks. Good. Question marks. When was equilibrium established in? Just from looking at the chart. Actually, at 5 seconds. And this is why I wanted to do it before everyone went. After 5 seconds, they remain the same. That's the first time that those constant values were there. Oh. Yeah. 5 seconds. Now, when we have equilibrium, what's equal about it? It sure isn't the amount, since that decimal 7, decimal 10, decimal 6. It's not the amount. I've mentioned this maybe before. But we have a forward reaction rate, and we have a reverse reaction rate. If it's going to be at equilibrium, no net change, that means the forward and reverse speed of reaction is the exact same. So what's the same? Forward and reverse reaction rates. I put Rx in as an abbreviation for reaction rates. Okay, moving along, and we're going to do equilibrium constant expressions. You jot this down. The general equilibrium expression is to have this reaction without balancing numbers, but that's what the small b, c, d, and stuff stands for. And this is the equilibrium expression. Write this out with the little exponents, and then I'll explain what everything means. Copying this stuff down. Oh. Great Jesus. Oh. So we've got this general expression. These represent the valence numbers. You notice they become the exponents. The valence numbers are the exponents. The square brackets, that means concentration in moles per liter. We just learned that earlier. And it's always the right side, the product, on the top. The reactants, on the left side, on the bottom. There is no addition on this. It's only multiplication, big line division as a fraction, right? So let's go through this. Using that, I'll get rid of this. We'll work through it. According to what's above. Write the equilibrium expression for this. Get up the reaction. We'll work. Well, okay, we got this down. All you're going to do is write down KQ. That K stands for like a constant. I guess like German. For equilibrium. So I draw a big line. I put my product on the top, right inside, SO3. Put it in square brackets. That means I'll put in concentrations if I have to. It's squared because of the balancing number in front of you. That's right. On the bottom, I put the left side, the reactant, SO2. The balancing number is 2, so I'm going to square it, times oxygen. That is to the power of 1, so I do nothing. That is my equilibrium expression. There's nothing you need to do if I say find the expression. Once we have concentrations given, we'll do values to put them. So, a couple of things about this. You don't have to write out this next page. We're just going to think it through and listen, okay? Don't write this out. Classes of equilibrium. 2 broad groups, homogeneous and heterogeneous. In homogeneous groups, same state, so all gases. Heterogeneous, okay, here's an example, liquid and gas, the same one. You'll often have aqueous and solids. Why is that important? Well, because be sure to watch, don't write everything out, for heterogeneous reactions, because pure solids and pure liquid states cannot appear in equilibrium. Why is that? It's because they can't change in concentration. Just think of it this way. If I had a block of iron, it's a solid. Oh, right, along like that. Anyways, if I had a block of iron, 100% iron, I'll take off this kind of erase. This is all iron. And then a reaction happens to it, and like a week later I come back, 50% of it's gone. Sure. But what's the concentration of this? It's still 100% iron right here, right? Would you agree? Solids don't change in concentration, even though the amounts change. This is why they don't appear in equilibrium expression. Same with pure liquids. So we only, and here's what you need to have. Only have aqueous or gaseous substances in the equilibrium expression. That's what you need to write down. And have pure liquid or pure solid. All right. Now, listen to this.
This is interruption. If you borrowed a school laptop, please bring it to the office now.
Back to this. Okay. Right. So this expression here, CaO plus CO2, double arrow, CaCO2. What's important about it is that this is solid. Can it appear in the expression? According to the rules? Nope. Gas? Yes. Solid? No. Only one of these is even eligible to be in this expression. Can't have this. Can't have this. So what is this expression going to look like? There's just one thing in it. AEQ. Products. Well, we can't have the product in here, so to hold the place, we just say 1 over. Never changes. And then CaO is not in it, solid, but CO2 is. That's it. It's the only thing that I do. Now we'll do the second one. Example CaCl, do that one. Break that one up real quickly. I got some questions for you. Don't worry about the last one there, so I'll just skip. Okay. So for this one, I want you guys to try it. We'll just go through it together. Well, okay, so let's see. My products have charges, so they go inside the bracket. Times Cl minus. Okay, this is it, because the denominator would have a solid. Make sure your charges are inside there. That's how they do. You're hilarious. Thank you for getting around. Video. Okay, you've had a chance to try these questions from L4. Here are the answers. I'll just scroll slowly. Pause then and get ready for L5. Okay. You should be able to find this as a handout. If not, hand copy this, but equilibrium constant value. Calculate the KEQ value of the following equation. Now, this is all given here, okay? But this time we're given concentrations in big M, which means moles per liter. So if you're asked for this, the first thing you do is write out the K expression. KEQ equals products over reactants. We just read. Should be hot on this. H2S in the square bracket. And there's a square because of the balance. S2 is a gas, so it's included. H2 squared as well. Then calculate the value. And I'm going to get you to use your calculator to do this because I use this one here. Well, because some people make a common error. So type up if you're making an error and I'll point out to you what it is. So put in my numbers. And you should get 0.179. Verify that. I'll know. If you're not, I know what it is. So ask me if you don't. Anybody not get decimal 179? Because I know what you're doing. You didn't? Oh, I heard you. All right. Oh, not. Okay, don't turn it back. Take the bracket of the where every calculator is different. You good? Good. Good. You're not. You're not getting 179? Right now. Wait. Okay. So that's you did fine. And then, you know, your method works. You good? Okay. Then moving right along. I was recording this whole time, so you have plenty of time to work on it. Underneath in red, no need for units on a KEQ value. A small K value means less than 1. The reaction favors the reaction. Why does that make sense? Well, we'll take a look at this mathematically. The products over reactants in words, right? The only way to get a small number of the products over reactants is if you have a number divided by the bigger number on the bottom, right? The reactants have to be bigger. It's the only way to get a decimal number. When you have small k values, like decimal 179, it means there's more reactant than there's product. The opposite is true as well. If you have a bigger k value, it means there's more product. Underneath here, this refers to something that you can have on hand in this. If you write a reaction in reverse, the k value is the reciprocal of the original k value. So, I'll show you what I mean. For example, that reaction above, the top, I've written in reverse, 2H2S, right? Gives you S2 and H2, 2H. Use that same concentrations as given the top to calculate the k value. Well, let's do this. So when I do that, I go K U is equal to now the product of the reactants is totally opposite. That's 2 on the top, H2 squared on the top, H2S on the bottom, but 2. So I'm taking this new one, right? I do my concentrations. So I've got 0.3 into formulas. And tell me what we get. Okay, what's the answer? Harmony. So let's go with 5.60, right? It's around. Yeah. Now, what we can do, we're not taking advantage of what I wrote in red. Use the same concentrations as my calculated K2 value. Fine. But if we were told to write the reaction and reverse the K value to reciprocal of the original, shortcut. There's a reason because I'm going to do this. Is the original at the top is 1.179, right? So K is equal to the reciprocal because it's written back. You notice how this blue expression here compared to the top? It's the same expression, but upside down, right? So wouldn't it make sense? It's the same K value, but upside down. Now, within reason with rounding, there's a slight difference for one decimal. What is 1 divided by 0.17? More or less, isn't it? Is it like 5 by 8 or something like that? So it's 5 by 9. Like, I mean, within one decimal place, there's two hundreds. Now, the reason I bring this up is on my hand-in assignment, which you guys are going to get started on in the next video, is the question where I say a certain reaction goes forward at this K value for the reverse. I didn't even give you the chemicals. All you need to know is the K value. Just put it, right? And then toss it into your calculator. A lot shorter than doing it with the blue one, right? Next thing. Another one. Or did you guys have this one? Yes, you do? Now, this reaction H2I2 making 2HI has K value of 50. Okay. Find HI if the hydrogen is 375, the iodine is 200,256. Well, we start again, same way. Write the KQ expression. I'll start it out with you. Everything's a gas, so it all appears. HI squared H2 I2. Then I substitute. In this case, we got K value given as 52. Finding HI squared. Yes, now everybody's from different math backgrounds. Some of you might be some of you will have taken workplace, so you don't solve as many equations. We need a hand solving this. Multiply everything up onto, say, the left side, 52 times 375 and the old 256. Get the HI squared along. I'll write this up. If you're good with this, just go ahead and solve. I haven't bonded with that multiplied vector. No, yeah. Which math did you take? What did you do if you got one? You're used to solving. You got a number for me?
Sorry?
You got a number for me?
It's 0.4992, so 0.5.
Hold on, let's go with 499 because we're going to square root.
Okay.
So you're saying all three of these numbers multiplied are 0.4, then what?
992.
Keep all of these. HI squared. Undoing a square means square root. Unless somebody's verifying, I'm not verifying these calculations. I think this kid is. She's smart enough to drop it on. I don't know what it is.
0.7.
0.7?
And then a 0.
Can you give it to 3 decimal? Like
Yeah. So 0.7065.
707.
707.
Now, I'm going to leave a space here. That's the HI. I would not, I give myself 2.5 out of 3. So, why? It's a concentration. It needs a unit. What's the unit of concentration? What's that? Nope, that's ground. Moles per liter. We can either put MOL over L. Maybe or else big L. It's the same thing. Going back to the start of the class where we talked. Now, some other notes you guys have. Now, I also mentioned KC. It's the same thing as KQ. Some books will use KC, some use K. Doesn't matter. Gives you a quick idea of the position of the equilibrium. I've mentioned this already, but no. A large K value, many products at the equilibrium. KQ around 1 means about the same. Small KQ, very few products at the equilibrium. Now B, the exact value of a K is dependent on temperature. So if you look it up in the book, it will say usually around room temperature. That's what most lab spaces are. But it'll be different at 100 degrees. It'll be different at 4 degrees. Since heat can shift in equilibrium concentrations, the KQ is listed at a certain time. But that's independent of the concentrations you start at. And the units vary from reaction to reaction, so we never use the units. So you can go up. Wrap